Good morning to you. This is lecture 18, the second lecture dealing with the third module on basic matrix concepts in this video course on advanced structural analysis. So we are doing the third module which we started yesterday. There was one topic remaining in a review of matrix algebra, that was dealing with eigenvalues and eigenvectors. We will quickly cover it. Then we will start looking at how matrix concepts can be applied in structural analysis. So this is covered in the second and third chapters of this book on advanced structural analysis. So eigenvalues and eigenvectors are something you have all studied while learning mathematics. What are the applications of these from your own experience so far in mechanics, for example? Have you ever applied it? You learned some technique in maths. Have you ever applied it? Never? Solving simultaneously, that is again in mathematics, but you do not have any applications in engineering, in mechanics? Well, think about stress analysis, finding principal stresses, locating principal planes. You have an application there. Think about buckling. You have studied buckling in mechanics of materials. You deal with an eigenfunction there, the buckled mode shape is an eigenfunction. So it really has a wide variety of applications. And one of the interesting applications is in solving simultaneous equations, you can end up diagonalizing the coefficient matrix A. How does that help making the coefficient matrix diagonal? You get directly, the solutions become uncoupled. They no longer need to be solved simultaneously, you can solve one at a time. So that is the ultimate way of solving these equations. If somehow you can reduce a coefficient matrix to its diagonal form, which you can do with the help of eigenvalues. So I will quickly go through this. If you recall, we said that any given matrix A can be visualized as a device that is capable of transforming a vector x whose components are unknown to another known vector c, which is your constant vector, through a linear transformation, and that is the meaning of this equation Ax equal to c. It is a transformation, okay. You are transforming one vector x to another vector c. Now where do eigenvalues come here and eigenvectors come here from whatever you have learned so far? What does an eigenvalue transformation do? What does it do in a physical sense? What will be the end result after you do the transformation? You get the same, you will not get the identical vector, you will get a vector which is a scalar product of the original vector x. What does it physically signify?
It is a vector which is parallel.
That's right, you get a parallel vector. So if A is a square matrix, then there exist certain special types of vectors x called eigenvectors, such that the transformation results in vectors that are parallel to x. Very simple. This means that the product Ax is a scalar multiple of x, and that multiple is often designated as lambda. It is called a scalar multiplier, and it is a unique property of the matrix A, and the word eigen comes from German, which really means one, unique. For a non-trivial solution, you see one solution is when x is null vector. The physical example that you can appreciate is the case of buckling, okay. How do you get the buckling load, the critical buckling load? Well, actually, if you remember, you must have done the Euler buckling analysis. You write down an equilibrium equation, assuming it to have buckled, and you try to find P critical, which would facilitate that buckled shape. So you will end up writing an equation where two solutions are possible. One is x is the displacement vector is a null vector, that means there is no buckling. The second is there is buckling. When you have a null vector, it is called a trivial solution. In the case of the column, it means that the column remains straight, remains unbuckled, and at a certain critical load, at what is known as a bifurcation point, two alternative equilibrium positions are possible, and it will prefer to buckle, so it cannot take any further load after that. So that is how important it is. Now to find a non-trivial solution, it is important that the matrix A must be non-singular. In problems of structural stability and dynamics, the square matrix A is usually symmetric, which makes our life easier, and this implies that all the eigenvalues will be real, not complex. There are situations where you have imaginary numbers coming in, but not in our real life problems in structures, and luckily for us the eigenvectors are going to be distinct, and they will be linearly independent and also mutually orthogonal. That is a property of the eigenvector. So in stability problems, the eigenvalues correspond to the buckling loads you have, and the corresponding eigenvectors, and they are referred to as eigenfunctions if you are dealing with a continuum. They represent the mode shapes of buckling, right. So you have the first mode called the fundamental mode, then you have the second mode, third mode, and so on. In practice, everything buckles in the first mode. We will study this in greater detail in the 7th module, but for now we cover the maths part of it. And in dynamics, what do you think the eigenvalues represent? In vibrations of strings, you may have studied in school, you have the first mode, the second mode of vibration, and so on, isn't it? So there the mode of, it is called a natural mode, the mode represents the shape, and it is similar to the shape you get in buckling. Say the flexural vibrations in a beam, you have the first mode, the second mode, third mode, and so on. It is a shape that you get, and what does the eigenvalue represent corresponding to any particular natural mode? They are called natural frequencies, and you have probably heard of the phenomenon of resonance. When the excitation coincides with the natural frequency, then you have large amplification in the response. So that is how important it is to study eigenvalues. There are some properties that I think you know. The sum of all the n eigenvalues of a square non-singular matrix A of order n into n, that means you have n eigenvalues, is equal to the trace, which is the sum of the diagonal elements of A, and the product directly gives you the determinant. So there is the properties of the matrix A are linked to the eigenvalues and the eigenvectors. So you can take a simple example. If the eigenvalue, you can prove this, that these two properties are real. You have probably come across this, it is called a characteristic equation, which is what you get when you want a non-trivial solution. Okay, the determinant of this matrix will have to be 0, which means the elements get shifted by lambda. You remember, you must have done this exercise, and you need to solve, you have shifted the lambda x to the left side, so now you have homogeneous solutions. Clearly for a non-trivial solution, A minus lambda I has to be singular, which means the determinant must be equal to 0. So this is how you have studied, and you end up with a polynomial equation of order n in terms of lambda. The roots are eigenvalues, and the corresponding x vectors which will not have unique components, since the rank of this matrix is less than full, you will have a linear dependence in the components of the eigenvector. So there are many ways of doing this, and you have probably studied some of them. One convenient way is to reduce this A minus lambda I to its row reduced form, and then you can easily find out, using the technique that we discussed yesterday, you can identify the eigenvector. Okay. Take an example, and you have done lots of these problems I think in your earlier semesters. This is what you do, you get a cubic equation in this case, which you can solve and identify the 3 eigenvectors. You put them in ascending order, so the first eigenvalue is the lowest, in this case the 3, 6 and 9. If you take one of them, lambda 1 equal to 3, if you locate its row reduced form, it is easy then to find the eigenvector. This is not the only way you can do it, you probably learnt it in some other way, but finally you will find that it is C by 2 C and C. Now C can take any value. So for example, in a pinned column subjected to an axial load, the eigen shape is a sinusoidal shape. The sinusoidal shape only relates every point's displacement to every other point's displacement, but it does not fix the amplitude. That is what is reflected here. C can take any value, C is like the amplitude of that wave. All that it guarantees is that all points on that wave have a definite relative amplitude. So that is the beauty of the mode shape. The mode shape does not dictate the absolute value of the deflection. Similarly you can do it for all of them, and you can normalize these eigenvectors, you have studied them. Commonly what we do is we take one of them, the top one, and make it unity and scale the others, but there are other ways of scaling, and once you have normalized it, you call it an orthonormal eigenvector. So a vector like this you can put together and you can get a matrix, and that is called the orthogonal eigenvector matrix, and it has certain beautiful properties. One of the properties of this matrix, which you see here, is that the transpose will be the same as the inverse. So finding the inverse is very easy, just take the transpose of it. For example, once you have identified Q for this matrix A, if you take the transpose you will get it, and you can also put the 3 eigenvalues together into a diagonal matrix, and that is called an eigenvalue matrix. It will look like that, and then if you do a little trick, Q, that symbol is called capital lambda, Q capital lambda Q transpose will give you back the original matrix A. That is a fantastic property, and what is the advantage of this property? This property helps you diagonalize the matrix A, because your A is your original coefficient matrix. So if you do that, you get back A. This matrix A can be factorized or decomposed into that form, and that procedure is called eigen decomposition. These are techniques used for solving simultaneous equations essentially, and if we do not use the eigenvector and we choose any other, I mean we do not use the orthonormal, we take any eigenvector, you can choose any eigenvector, then you will end up with a symmetric matrix, and then also factorization is possible. Commonly when we apply to real problems of finding buckling loads and so on, we have a slight shift in the formulation. Instead of saying Ax is equal to lambda x, we sometimes encounter the form Ax is equal to lambda bx. Okay, we will see this, how this happens later, in which case you get A minus lambda b into x equal to 0, and you need to solve this equation, and typically x corresponds to the displacement vector, A corresponds to the primary stiffness matrix. So there is a strong relationship between the stiffness matrix and the mode shapes and the eigenvalues, and lambda b corresponds to the geometric stiffness matrix, which is something we will study in module 7. Just want to show you that mathematics is a very powerful tool in structural analysis, and it is good to know at least conceptually what is going on. You need not do any eigenvalue longhand calculations, the computer will do it for you. You can use those tools, but at least broadly you should never forget the background, what is going on under the black box. So there are many iterative methods. In our times we had to really manually solve all these and learn all the techniques and find out which is the most efficient. So there is a power method, Jacobi's method, Stodola-Vianella method, and so on, and commonly we had to do this whenever we studied buckling, instability or dynamics, okay, where you have multiple modes to be considered. So with this we conclude the maths part of it, which is just a refresher. Now we get into how to apply matrix concepts to analyze structures. Now remember, we have 7 modules. 2 modules was basic structural analysis, which you do manually. This third module is basically introductory. It is the 4th, 5th and 6th where we directly apply matrix methods to problems. In module 4 we apply it to trusses and axial systems. In module 5 we apply it to beams and grids. Grids are 3-dimensional. In module 6 we apply it to plane frames and space frames. In module 7 we do instability and second order analysis. You will find that these concepts really start making sense only when you start applying them. So what we are going to do from now on is only kind of introductory. We are kind of planting seeds which will take a little time, a gestation period for them to germinate and learn. So once you start applying, it becomes very easy. So if you do not fully understand at this stage, do not worry, it will all fall into place as we go on. So the topics we are going to cover is introduction, coordinate systems, and these look simple, but you will realize that the first difficulty you encounter is how to convert all that you have been doing on paper, drawing a truss or a frame, how to pass it on to the computer. So you need to have a coordinate system, you need to have a framework in which you can put that structure and identify everything that is going on in the structure. So that is how important coordinate systems is. Then you need transformation matrices. What do you think these mean? Essentially you will find you need 2 coordinate systems. When you run a country like India, you have a central government, the federal government, and you have state governments, right, and you have to have some control between the center and the states. Likewise in a structure, the structure is one, like the country, the nation state India. So the structure must have a federal coordinate system, we call them global coordinate systems, okay. So the entire structure is located in a global framework with one x, y, z. But then when you get to the element level, the element may be inclined and located anywhere, it is better to go in for a local coordinate system, the state government, and transformation is all about switching from the local to the global or the global back to the local. So that is very beautiful. It is really transforming, it is a linear transformation from one system of Cartesian coordinates to another system, okay. Then we need to look at stiffness matrix. Again here you can define the stiffness matrix at the element level and you can define the system matrix at the structure level. What do you think is the difference?
One element, the entire structure.
Like what is going on in your hostels, you have these groups, the Andhra group, the Karnataka group, and the Kerala group, and the Maharashtrian group, and so they are all element level groups, but we need national integration. So we need to connect the groups together and make us live harmoniously. If you do not do it harmoniously, you will have separation, you have lack of compatibility, which is the cause of much strife in the world today, right. So similarly in a structure, unless the members they can have their independence, but unless they operate together harmoniously in the interest of the overall structure, you will have problems. So similarly you have to understand stiffness matrices, flexibility matrices both at the element level and how it all fits in at the structure level. And you have already studied this. Whenever you encounter intermediate loads, because you want to limit your degrees of freedom, you have to pass them effectively to the joints, so you need equivalent joint loads and you need to find fixed end forces. Now we will also look at 3 different types of methods. You have a stiffness methods which again branch out into 2, which we are going to call conventional stiffness method and reduced stiffness element stiffness formulation, and flexibility methods. We will see this shortly. But first let us review what we have learnt already. I have shown this picture earlier. If you take a truss, identify its degrees of freedom, you will find that they are D1, D2, etc. And at the corresponding locations in the same direction you can identify forces, we call them F1, F2, F3, so on. These are so called external forces and joint displacements, they affect the structure as a whole, that is the central government, okay. But at the element level, you pull out one of those truss members, that element has its own internal force, okay, which we will locate at the ends of the element, okay. You have 2 forces at the 2 ends, and somehow these forces are linked to F1, F2. So actually you have a transformation there itself. How do you convert joint forces on the structure to element level forces in different elements? You see, you can see the potential, and the basis for that must be equilibrium. Similarly, every member in this truss can elongate, the 2 joints can move. Compatibility demands that whatever movements you get at the element end levels must match the movements you get in the structure. So 2, 3 elements joining at one point will have the same movements in the global coordinate system, but in the local you have to resolve them into their relative components. That is compatibility. And structural analysis is all about getting a good grasp of these, knowing what is happening in your force field, knowing what is happening in your displacement field, and defining the laws that relate these fields. Once you have got a good big picture understanding, you can program everything, the computer will handle everything for you. We are lucky we are dealing with linear analysis, so the transformations are all linear, there is absolutely no problem. So let us begin with the basics of coordinate systems. Let us say I have a structure like this, okay. I have made it, I made it a little complicated in the sense you have inclined columns, which you know are the more complicated types of problems you can get. And I have a structure here, it is a plane frame. I first need the computer to kind of get hold of the structure and be able to draw it back to me, and so that I can confirm that this is exactly what I want. So I need to have a coordinate system first to identify the joints in the structure, right. So I first choose an origin. In this case I could have chosen, usually you choose the extreme lowermost left end, okay, but you can choose anywhere on that plane. So I put it somewhere there, and that is my origin, and I have x and y. Conventionally x is pointing to the right and y is pointing upwards, and that automatically defines z, okay, or as the Americans say z. You have to follow the rules of vector algebra, which means I cross j must be equal to k, and if you follow the right hand corkscrew rule, you will find that z will be coming outside towards me from that plane of xy, okay. So if you try to, these arrow marks hold not only for forces and translations, the double arrow in the same direction holds good for moments and rotations. So you will discover the z positive direction will demand that I should consider clockwise or anti-clockwise rotations to be positive. Anti-clockwise. So this is the first change we are going to make from what we have studied till now. Okay, it's a big change, it's an abrupt change, because till now in displacement methods we assumed clockwise rotational moments to be positive, because that's the way traditionally it was done. You know, slope deflection method, they evolved like that. But today we have a big picture, proper grasp of it, we want to apply matrix methods. It should be consistent with our idea of what is positive. So we make this change, and we should do it little effortlessly, and it's like getting an international driving license. And you know that in some countries including India, you have to stay to the left side of the lane, but when you cross over to another country, there you have to be on the right side, and you are okay with it. So then only you get the license to drive, then only you get the license to apply matrix methods after having studied basic structural analysis. So having done that, you should first write down the coordinates for A, B, C and D, which is easy to do. If someone has given you the geometry of the structure, you can do that, x, y, z of A, B, C. Well, some people don't like to use any letters at all, so they will call those joints 1, 2, 3, 4. It's okay, but you have too many 1s and 2s, so I thought in the early stage it's better to do this. And then you have 3 elements, so you should identify the 3 elements, the 3 states. Okay, this is a country with 3 states, element 1, element 2 and element 3. It's clear, and I put a circle around it so that I don't mix up with some other numbers which are going to show up soon. What's the next thing I need to do? By the way, there is something more to it. To define the element, you also have to define the orientation of the element. What is the start of the element? What's the start node and what's the end node? Okay, so that's you have a choice there. But if you move consistently from left to right and from below to above, then A to B it's called the incidence of my defining element A, element 1. B to C is element 2 and C to D is element 3. So I need to do all this. I need to first locate A, B, C and D. I need to identify elements and their start node and finish node, and then I've got that. What more do I need to do? So those are called nodes. Nodes are locations where you need to locate either a displacement or a force. So you can have nodes inside an element. If, for example, if you have a concentrated load and you don't want to convert to an equivalent joint load, or you want to find the deflection in the middle of a member, you can create a node there. Nothing prevents you from, but the moment you create a node, you've got 2 elements joining that node. But we shouldn't make life more complicated than is necessary, so we normally limit the nodes to the joints. Okay, but nothing prevents you from bringing in additional nodes. So you define elements and nodes, and next you need to define degrees of freedom, right? We are primarily doing a stiffness formulation, later we will look at the flexibility formulation. So the degrees of freedom here are in this plane frame, you know, at B and C you have 3 degrees of freedom, and let us align those along our chosen Cartesian coordinate system. So along the x direction we say the translation is 1, along the y direction positive upwards is 2, and anti-clockwise rotation at the joint B is 3. Does it make sense? So we know that every joint you potentially have 3 degrees of freedom, 2 translations and 1 rotation. D1, D2, D3 would mean that. But then you move on to the next joint from B to C, because you have only active degrees of freedom at B and C. At C, what are your coordinate numbers, if you finish 1, 2 and 3, you need to do 4, 5 and 6, okay, you need to do 4, 5 and 6, right, and that is all you have, or do you have more, do you have more degrees of freedom? Yes, at D also you have some more, that is a roller, so it can move, you have an active degree of freedom there, so it can move to the right and it can also rotate, right. Now you can choose 7 and 8 there, is it clear? Then what else do you have? Then you have, if you want to take care of support reactions, you need to have, or you have support movement. So to complete the picture you should also look at what is called as restrained degrees of freedom. So you do that, so you can bring in 10, 11, 12, 9, 10, 11, 12, got it? These are the restrained degrees of freedom, 9, 10, 11, 12, right. You can do something, I have changed the color here, but when you do it by hand there you are probably using the same black or blue pen. So there is something nice you can do to identify restrained coordinates. You can just introduce a slash in the arrow marks. The slash tells you that that degree of freedom is not active, it is restrained. When you use software packages you have to feed, it is a binary code, you have to show whether it is restrained or it is free to move. So normally the numbers are 0 and 1, okay, 0 and 1. So here we are doing this. So with this we have captured all the displacements at the different joints D1 to D12, some of them are active, some are restrained, is it clear? And by the way, restraint does not prevent you from including support settlements, but then you say that it is still a known quantity, usually it is 0 but it can be non-zero, okay. So you can define a displacement vector dA and dr, which I can partition like that. I am putting all the restraint at the end of the list, is it clear? The D vector, the displacement vector, have displacements at active degrees of freedom, active coordinate locations, and R stands for restrained coordinate locations. Now luckily A and R also have other words to describe it from a force point of view. So you can also have FA, which is conjugate with dA, and FR, which is conjugate with dr. It is exactly where you have active degrees of freedom that you can apply loads, isn't it? So A stands for actions, which means loads. So you have FA corresponding to dA, and it is exactly where you restrain displacement you get reactions, and luckily for us R also stands for reaction. So FA, FR constitute our force vector in the global picture, and dA, dr constitute our displacement vector in the global coordinate system. Does this make sense? Okay. Now the word coordinate has two meanings here. We are referring to 1, 2, 3, 4 all the way to 12 also as coordinates, and the Cartesian coordinate system that we use are also coordinates. So you have to be careful in interpreting the word coordinate. Does it make sense to you?
So at the joints we have to provide constraint, like both can rotate freely about that, or both has to rotate at same theta.
No, if you do not say anything, we assume you are dealing with a rigid joint. For example, member 1 and member 2 are rigidly connected at B if you do not make any statement. If you want to, and if you are dealing with the ends, boundaries, there you have to define the supports. Is it free or is it restrained? But you can have more complications which we will introduce later, not in the beginning. Supposing I have an internal hinge, then it is little difficult, we will study that later, okay. We should begin simple, then we will get into complications, but it is a point how you can bring in releases, but as beginners let us not introduce those complications. Let us take simple problems, straightforward problems. Do you understand this? Is it clear? Okay, let us demonstrate how it is done. Let us take the same frame, and the physical meaning of dA and dr is shown in this vector. You will find that the first element in this vector d1 actually points to delta bx. That means at this joint B, if this moves to the right by some quantity, that component of the deflection to the right is called delta bx. d2 will be the amount it moves upward, right, at B. d3 would be the anti-clockwise rotation here. If you end up with a clockwise rotation, you should put a negative sign. Likewise, you can cover all the way from d1 to d8, okay. Then you are left with d9, d10, d11, d12. Those are restrained degrees of freedom, and unless you include support moments, they are tacitly taken to be 0. Is it clear? No doubt about that. Now in this problem you have 8 active degrees of freedom and 4 restrained degrees of freedom, totally 12 degrees of freedom. Fine, very clear, no problem. Let us look at a problem where you have some loads applied. How will you write down the force vector? So I have in this problem 3 loads. So what would you call 50 kilonewton? What is plus 50 kilonewton? Huh? It's, yeah, you should talk in the language of the coordinates. F1 is 50 kilonewton. What is 100 kilonewton?
Minus.
Yeah, so F2 is minus 100. And what corresponds to 75 kilonewton meter?
Minus.
Yeah, F6 is minus 7. And what about the others? They are all 0 on the action side. FA, so FA is exactly what we said. You correctly said plus 50, minus 100 and minus 75, the rest are all 0, because though those joints have the potential to take loads, for this particular load case those values are 0, and the reactions are not 0, but they belong to the unknown category. That is part of the response and we need to find them out, right. Does this make sense? Very simple, we are going in baby steps, this is very straightforward. Now we also recognize that there is something called a stiffness matrix for the entire structure, which means if you tell me that I have on account of that loading I have a displacement vector d, then the force vector that caused that displacement vector must be F, and they are related by this equation F equal to kd. If the displacements are unknown, then I can easily get the displacements by inverting the force, but it is not so simple, because you will find that in the vector F you have Fa and Fr. Fa is known usually and Fr is not known. Similarly in the displacement vector d you have dA and dr. dA is not known, dr is known. So you can't apply this directly, you have to play with it, and we will see how to play with it. Now we will switch from central government to state government. So how do we do that? What do you suggest?
Write equilibrium equations. Equilibrium equations for this.
No, we are talking about coordinate system. See, capital of India is New Delhi. Do you want the capital of Tamil Nadu also to be New Delhi? Where do you want it to be? You want it to be here at Chennai, right? You want to be the boss. This is your origin, this is your capital. So this becomes your reference point. New Delhi talks to Chennai, and the whole of Tamil Nadu is governed by Chennai. So your coordinate system, your origin should be, so you have the choice to choose where, I mean you usually put it in the middle of the state, but we do not usually put the origin in the middle of the member, right? Where would you like to put the origin? Which one do you prefer? A. Okay. So that's what you do. You start the origin at A, then you don't align your x and y in the, why should you follow what Delhi says? You choose your own local system, right? So, but if I write the same x and y, there will be confusion. So when I am dealing with a local coordinate system, I put a star, I put an asterisk, okay. So whenever I put a star, what does it tell me? I am dealing with local coordinates, not global coordinates. Is it clear? So I have x star, y star for element 1, and I have to finally link it to the global, because the x and y global I have shown below here. This x and that x have to be linked. How do I link it? By the relative rotation. If they are parallel, theta is 0, right, and I have to choose a direction, so I consistently choose my anti-clockwise direction. So this is my, once I define theta x1, everything is defined. I know how y is oriented with y star. Is it clear? Now having done that, I can do it for other states, right. So I go to member 2, I do the same thing, but now I say theta x2 and theta x3. So the elements have L1, L2, L3 as their lengths, assuming they are prismatic. If they are not prismatic, let us say you have a stepped element, then it is worth creating a node wherever the step is taking place, right, and treat that as a separate state. So you have, is this clear to you? Now what is the next step, next thing we need to do? We need to again bring degrees of freedom. How many degrees of freedom do you have at any joint, any node? 3. So let's, can we choose it this way, 1 star, 2 star, 3 star, 4 star, 5 star, 6 star. You agree that these are independent, so I have 6 degrees of freedom for a plane frame element. What do I label for the element 2? Should I do 7, 8, 9? No. Yeah, I will stick to 1, 2, 3. Okay. I am only saying state number 2. Does it make sense to you? Clear? Central government, state government, global, local. Good. Now what? Now for each element, for the ith element, let's say, this is a simple structure with 3 elements. I can have a structure with 525 elements. So I is a generic index that I will use. So I define, now this is the definition I use. If I say D without any star, it goes to central government automatically. So I have to put the star, I can put it above or below. I am putting it below because I need to have other indices, and I am putting my I here. I can be 1, 2, 3 to distinguish between the 3 states. So does this make sense to you? So I have a displacement vector 6 by 1, and I have a corresponding conjugate force vector. Does this make sense? Okay, so now I have created a framework with which to start playing my game, but without creating a framework which all of us share and understand and agree to, we will have problems. So is this clear? Is the notations clear? Okay. By the way, different books give different notations, shouldn't get confused, the concepts are the same. So you have to define the local axis, you have to define the start node, you have to define the end node, and everything falls into place. The theta is crucial here. Okay, now you can also combine all the elements together and put them all in one group. Okay, for example, I call a combined element displacement vector D star without the I, which means it includes D1 star, D2 star, D3 star. Each of these is 6 by 1. So what is the size of this one element? 18 by 1. If I want to, okay. If I have 525, I won't waste time doing this because it is too complicated. But 3 elements, maybe it is nice to put them all together, put all the guys in one line. Similarly, so that is clear. Similarly, I can do for F star. Is it clear? So this we will call the combined element displacement and force vectors. It is optional. You may never need to do this, but sometimes for small structures it is good to put them in one line. Okay. Now the element has its own governance, right. So at the element level you have a relationship between the element force vector and the element displacement vector, and you can talk of an element stiffness matrix in the local coordinate framework. Does it make sense? So you have an element stiffness matrix unique for each element in that structure, and you have a common structure stiffness matrix, and obviously the element stiffness matrices contribute to the structure stiffness. Does it make sense? How do you put it all together is what we are going to study. Take a look at this. I am showing you 3 examples from a very good book by Qasim Ali, where he shows how we can do the numbering in an optimal way. Numbering of global coordinate system. Here I have shown you a continuous beam, a 7 span continuous beam, right? 1, 2, 3, 4, 5, 6, 7. How many degrees of freedom do we have? What is the degree of kinematic indeterminacy?
1, 2, 3, 4,
6.
5,
It's a B.
6.
You have 6 rotational degrees of freedom. Okay, I didn't write A, B, C, D, but they are there. How will you number them? Well, it's straightforward here. You number them sequentially like this. Remember, anti-clockwise positive. Okay, earlier we did clockwise positive, but now we are doing anti-clockwise. 1, 2, 3. This is fairly obvious. Supposing I do in a funny way. I put 1 here, then I choose to put 2 here, then I put 3 here. What do you think will happen to the stiffness matrix? It's a good question.
It will just shift the columns.
Let me ask you. You were temporarily not in the class. What do you think will happen to the stiffness matrix? Just to wake you up. It's an 8 o'clock class and half of you are half asleep. Tell me. Anyone?
It will just shift the rows or columns.
What will happen to the type of matrix you get?
Same matrix, but same numbers, but elements will.
No, some beauty in that matrix gets corrupted. What gets corrupted? Symmetry will. The stiffness matrix has to be symmetric. We proved it. It won't be banded. It will be all over the place. It doesn't look nice. You can't put it nicely. So you want to make it banded. It may still be banded, but the bands are far, I mean, you are pulling in bands stretch to the extremes. You don't want that. So it's important to keep your band small, and there's a measure for it. It's called bandwidth or half bandwidth, and these are your restrained degrees of freedom. So let's just look at the active degrees of freedom. You forget about the restrained degrees of freedom. Incidentally, you can partition your K matrix into active and restrained components using these notations. Does this make sense to you? If I have F as FA and FR and D as DA and DR, I can write K as KAA, KAR, KRA, KRR, which means FA is KAA into DA plus KAR into DR, right? Now if DR is 0, then the equation is simply FA equal to KAA into DA, which is the most common way of dealing with the stiffness matrix. Is it clear? So let us look at KAA, and you can find DA from that. If you look at KAA, if you do this numbering system, you get a beautiful band like that, and the half bandwidth, as it's called, turns out to be 1. That means you have the principal diagonal, you have to take only one more cell to the right and to the left of that principal diagonal. That's fantastic. It cuts down your computational work and your storage to a high degree of efficiency. I am not saying you need to do all this in your class assignments, but when you are actually doing structures or when you are doing programming, it's important to figure out how best to do this. So let us take a more difficult structure like a truss or a frame. Now you will find you have 21 degrees of active degrees of freedom in the truss and 24 here. We will figure it out later. Let us take the frame. Every joint has 3. Let us include axial deformation. How many free joints do you have? 8. 8 into 3, 24. Clear? Similarly for that truss. So is there an optimal numbering scheme? What do you think would be the best way to do the numbering so that you still get, you minimize your half band width, because that helps a lot. nearby places. So the number of arithmetic operations involved in solving a set of equations increases linearly with the square of the half bandwidth, and to minimize the bandwidth of stiffness matrix the numbering sequence should be done along the shorter direction of the structure. This is what we did in the previous example. So this really means if these are your active degrees of freedom, number them 1, okay, you got 1 here, 2, 3, then don't go here, don't go along the longer direction, go along the shorter direction, 4, 5, then you can either go here or here, 6, 7, 8, 9 and so on. Does it make sense? If you do it this way, you will get a banded matrix which looks like something happened, which looks like this. It is a symmetric matrix, the half bandwidth is roughly 1/3 the degree of indeterminacy. That is very good, it is a neat arrangement, okay. And if you take the other example, you should number them this way along the shorter direction, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9 all the way here, you got 24, and when you look at the matrix it looks like that, okay. You might still get some 0 cells in between, but you can't get it less than this. So the half bandwidth is 1/3 NK, turns out to be 8. Any questions?
After 1, 2, 3,
Yeah.
we are not going up, but we are going in the
You should go along the shorter direction always. That's the
column is shorter than the
not that way. You look at the bay, the overall size of the structure. Okay, it's not the height. The lengths of the members don't matter at all. Lengths don't matter because they are just properties. It's so this is an important lesson to learn. We'll stop here. Thank you.